Leetcode 210, course schedule 2. It's very similar to course schedule 1. And again, it's medium question, but could be hard as well. So because we've already solved course schedule 1 on my channel, if you have watched that video, then you can skip to the end and just see the coding part if you don't want to repeat all the theory again, since it's similar. Actually, the only thing that's different is that inside that problem, we have to figure out that they are talking about topological sorting. And in the first course schedule 1, they wanted just to get Boolean answer. Is there a valid topological ordering for given input? And here they want to have the ordering itself. Yes. So as you traverse graph, as you sort through graphs or other hierarchical structures, you can either just move through your paths that you are exploring, or you can also add some additional variable, some auxiliary variable that will keep track of every node that you have visited, and then in the end you have some kind of path that you can share. And that's exactly what they want here. So usually they just want a single yes or no answer, or some counter, for example, how many nodes have you visited, but in this case they want to have the whole path. So that's more or less it, but let's read it again just for the sake of it, or if you are just interested in course schedule 2. So there are a total of num courses you have to take. Yeah, so those are our courses that theoretically we have to take into account, and those are just numbers. And so there are no courses like math, English, history, and so on. Those are numbers from 0 to num courses -1. So 0, 1, 2, 3, 4, and so on. And the input that we have, besides this single integer num courses, from which we have to extrapolate that there are that many courses and what they are, those integers up until this number, there is a second input called prerequisites, which is a list of pairs. There is A and B in each pair, like 2 elements, of course, and those 2 elements are taken from this set. Yeah, so A and B have to be between 0 and num courses -1. So those are the relationship between different courses. And what kind of relationships? Those indicate that you must take course B if you want to take course A. So A is child and B is parent. Yeah? In language of graph theory, because that's really what it is. This is a graph, since graph model relationship, or can be used to model relationships. And here is an example. For example, the pair 0 to 1 indicates that to take course 0, you have to first take course 1, return the ordering of courses you should take to finish all courses. If there are many valid answers, return any of them. If it is impossible to finish all courses, return an empty array. Yeah, so in the first course schedule 1, we simply checked if as we were sorting our graph, we were increasing a counter in each iteration. And if the counter was equal to this number, num courses, then we returned true, and otherwise we returned false. Yeah, so we just put this condition at the very end. And here we would have to check the length of our path. As we will be sorting, we will be constructing a path. And if the path is, if its length is equal to num courses, so if it has that many elements, that means that we found one valid ordering and we can return it. So any valid ordering is a correct answer. And if it's different, like if the number of elements is any different than number of courses, that means that there is no valid ordering and we have to return an empty array. And here 2 examples. Last time there were like some smaller examples. This time the second one, there's also third one. Yeah, the second one at least is a bit more interesting. So usually when they just give you like a single input or something like that, very small, you cannot really get all the edge cases that can come with given tasks. So I prefer when they give some at least a little bit something a little bit bigger. That's how example 2 looks like. So that's interesting, but let's start with example 1. So we have number of courses is 2, yeah, and the valid courses are 0 and 1, and there is one relationship prerequisites: 1 is child and 0 is parent. Yeah. So if we were to draw it, 0 goes to the top, that's our parent, and 1 goes here, bottom, and that's the relationship. First we have to take 0, then we can take 1, and the valid order is 0, 1. Yeah, so there exists a valid order exists. Let's phrase it like this, and that's it. Nothing more that we can do here. We can mark it as correct. And the second one is a bit more interesting. So let's see. It has 2 valid ordering. So let's see if we can graph it. Let's put it here. That. So again, the first element is 1 child, 0 parent, like this. And then the second, 0 is child, as well. No, 0 is the parent and 2 is child in that case. And then we have 3, which is our child, and 1, which is our parent. All like this. And then 3, which is our child, and 2, which is our parent. So that's our graph. And can we get an order, valid topological order from this? Yes, we can, because there is a place where we can start and there is a place where we can end. And how can it go? For example, we can start at 0, then go to 1, go to 2, and then to 3. Yeah, and then we will always have valid order. And we won't violate any constraints when it comes to our course prerequisites. And that's one valid. And there is, I think, some other. So let's see, 0, 1, 2, 3. This is the same that we have. Yes, that's the same. And the other one is this. Let's copy it as well and take a look into it. There is as well 0, 2, 1, and 3. Yeah, of course, because we can go either first to 2 or 1, because both of them are children of 0. That's both of those make sense. We can also make the list here. So that's the format they're expecting. And the last one, there is one course, but the prerequisite is empty. So of course we cannot have a valid topological order because nothing is here. No, we can. Sorry, we can because there is no loop or any invalid gaps. So we can just take the course 0. Well, in this case, it's also valid. That's interesting. So first I thought that it's invalid, but after giving it a little bit of thought, it seems that I was wrong initially. Good. So now let's think about this topological sort. And as usual with topological sorting, we use Kant's algorithm. And for that purpose, we need to gather so-called integers. Yeah? An integer is just the number of arrows that go into our node. So for 0, that is 0. For 1, it's 1. This arrow goes here. And for 2, it's also 1. And from 3, it's 2. There are 2 arrows going from here and here to here. And why do we need it? Because in order to get a valid topological ordering, we need to start a valid point. And the only valid place where we can theoretically start is place which have no other dependencies. Yes. So in the language of trees, it would be our root. And only this is a possible place where a topological ordering which is valid can start. So other than that, there is no sense in exporting, for example, starting from here, because this one has already a dependency. So we want to start in a place with no dependencies and then explore from them. And that's how we can traverse the whole graph in an efficient manner. Yeah, and as we traverse, we always remove even dependencies. So for example, when we first move to 0, then we remove it from our graph. We decrease in degrees. Here 1 goes to 0 and 2 goes to 0 and so on. And we go to the next valid entry point. And that's how we progress. And in the end, either we have traversed the whole graph or not. And if so, then there is a valid topological ordering. If not, there is none, and we have to return an empty list in our case. So that's the most important part. And additionally, we also can keep track of adjacency list, just to get all the neighbors in an efficient manner. So in this case, adjacency list would look like that. So 0 would have 2 neighbors, 1 will have 1, and 2 will have also 1 neighbor, and 3 will have none. And that's it. So we need to create in degree, we need to create adjacency list, and then construct a queue based on the in degree by giving all the elements with in degrees of 0, first adding them to the queue and then decreasing as we progress. And as we progress, also we need to have some variable that will keep track of our path that will return at the end. Okay, so let's start coding. And first things first, we need our adjacency list, and we need our in degree list as well. This is a 2D list. So for each node, which is each node is each course. So how many of them there are? For underscore in range number of courses. Yeah. Here we are preparing that each one theoretically has possibility of n other neighbors. Yeah. Or, including itself. And but for now we'll leave it empty, and we'll fill it as we iterate through the prerequisite pairs. And for in degrees, first we give 0, also n times, but this is a flat list, because for each one we don't need a whole list. For each one we just need a single number, and we start with zeros, and as we will iterate through it, and now we can start this iteration. And prerequisite pairs are first is children, and then is parent. So first is course, and then is prerequisite. Yeah, so we can iterate through it in the following manner. And now we can fill both adjacency list. Let's copy it. And adjacency list of course. No, of prerequisite at course. Well, it's in this direction, because it's a directed graph, and here in degree of our course plus equal 1. And so increment by 1. And now we need to queue using dq one imported from collection. And what's inside? So we want courses for course in again in range, and here I forgot in range number of courses. Need to get all the courses, but only if in degree of course is equal to 0. If this is a valid starting point, and while q is non-empty, we'll be doing something, and in the end we will return something. But what's the something? So here is path that we will take, and in the end we have to check. We can return path if the length of path is equal to what? To number of courses, and otherwise an empty list. So either like this or like this. And here we have to take course from our queue, pop left, and append it to our path. Each time we do the iteration, and now we have to go through each dependent courses. So for depend for child in adjacency list, have to copy it since I cannot write. It's too difficult for me to do it without mistakes, so I have to always copy adjacency list of course. And here we need to decrease the in degree of given child by 1, since we used its parent or its prerequisite course in the language of that problem. And then we have to check if, for example, if it's equal to 0. And why? Because in that case it's a valid next entry point, and when we can add it to our queue. So queue append child. That's it. So let's try. Probably I made some mistakes in the code. Yeah, as usual. Second time the same shit. I did it also last time. Sorry. Pop left. Okay, that's it. So the first 3 cases are correct. There is a chance for having correct all cases. Amazingly enough, we beat 100%. It's a bit suspicious, but let's leave it like this.